Okay, here what we are going to do is we're going to determine the gravitational field constant at points A, B, and C relative to the Earth's surface. Now remember, the gravitational field measures how the mass of the Earth affects the surrounding space, so that other objects with mass will experience a force exerted at a distance from the Earth. So if we look at A, we take A to be essentially the surface of the Earth. So remember, we have to place a small little test mass there. Okay, and we take the operational definition of the gravitational field, which is G is equal to the force of the source, in this case, which is the Earth, on the test mass, divided by the test mass itself. Well, this force here is a gravitational interaction between two objects with mass. So the two objects would be the mass of the Earth times that little test mass, divided by the distance between them squared, divided by the test mass. Okay, we divide out the test mass, and we are left with G times ME over R squared. Okay, if we substitute all this in, we get 6.67 times 10 to the negative 11th times the mass of the Earth, 5.97 times 10 to the 24th kilograms, divided by the radius of the Earth, 6.38 times 10 to the 6th squared. Okay, we calculate this out, we get 9.8 approximately newtons per kilogram. Not to really anyone's surprise, on the surface of the Earth, we've known from quite a while already that the Earth pulls with 9.8 newtons for every kilogram of mass. Just to kind of make a quick little point here, I'm going to highlight this in a different color. If we look at this value here, this is the value that equals 9.8 newtons per kilogram. Now, if I just take this value and look at the gravitational force itself, so basically this term, we find out that we have 9.8 newtons per kilogram times the test mass. Well, this is pretty much the force of the Earth, or the source, on our test mass, if we were to calculate it here on Earth. Okay, I just really want to kind of make this point that, we've been using this all along, and this is really where that little G comes from. I would first calculate it in the lab by measuring masses on spring scales, but this is where ultimately it's calculated from. Alright, for part B, we are going to add a height of 4,000 kilometers, or 4.0 times 10 to the 6th meters. So if we add that altitude to get the height at point B, the center to center distance at point B will end up being 1.038 times 10 to the 7th, yes, that's right, 7th meters from the center of the Earth to point B. Okay, so looking at part B, looking at the calculation to find the G field here at B, okay, it is going to be the force of the source. Remember, the source again of the gravitational pull at point B is going to be the Earth, divided by the small test mass we placed there. Let's put a little test mass here. Okay. Alright. This will be G times the mass of the Earth times the test mass divided by the distance between them squared, divided by the test mass. The test mass will divide out. We are left with G and E divided by R squared. Okay, if we substitute the numbers in but change R to 1.038 times 10 to the 7th meters, we're going to find out that we have a gravitational field of 3.7 newtons per kilogram. So compared to on the Earth, 4,000 kilometers from the surface of the Earth pulls less. This should not be a surprise that we know the gravitational interaction is based on the distance. The farther the distance is, the smaller the gravitational interaction, which means the field itself, the Earth's influence on the surrounding space, should also have a smaller value than that on Earth. Alright, now for the last part, part C. Determine the altitude above the Earth's surface where the gravitational constant is 1.5 Newton per kilogram. Okay, so in this case, we know that I'm going to start with the G field at C. I will skip writing out the force of the source on test divided by the test. I will also skip substituting in the gravitational field. We'll come right to here. So this will be capital G times mass of the Earth over r squared. Okay, since I'm looking for the distance here, or the altitude in this case, I have to solve for the distance between the Earth and point C. So we place a little test mass there, set this up like usual. Then, once I find the distance between the center of the Earth and part C, I can subtract out the radius of the Earth to find the altitude above the Earth's surface. So I'm going to rearrange this expression. I'm going to multiply both sides by r squared and divide by the gravitational field at C, which will leave me r squared is equal to G times the mass of the Earth divided by the gravitational constant at C. Substituting these numbers in, I get 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24th kilograms. Divide this whole thing by 1.5 newtons per kilogram. Okay, this will equal, oops, almost forgot, take the square root. Still have to take the square root of this whole thing to get r by itself. Okay, so if I take the whole square root of the whole thing, I get 1.63 times 10 to the 7th meters. Okay, now to subtract out the radius of the Earth. So 1.63 times 10 to the 7th meters minus the radius of the Earth will equal, that's a terrible R, 9.91 times 10 to the 6th meters. Okay, so that is the altitude above the Earth's surface to get a gravitational field constant of 1.5 newtons per kilogram, where the Earth only will pull 1.5 newtons for every kilogram. So if you had a mass of 100 kilograms, the force of the Earth would only be 150 newtons on you at that point.